Original schedule. First is Raffaella, Northwestern.
Right.
So I'll say you two.
Yeah. Okay. So I totally remade what I thought I was supposed to talk about. So because I realized that not many of you maybe knows what is going on in the scientific collaboration, on the LSST scientific collaboration. So there are 8 of those groups, scientific collaborations. And one of those, the most relevant to us, is the Transient and Variable Star Science Collaboration. And just to give you an idea of all the other topics, okay, all the topics that we are trying to cover, here is what we have. We go from galactic science, the supernovae, we try to do cosmology with LSST, and anything you can think about. But for today, the 2 things I want to draw your attention to is to the presence of 2 subgroups, the gravitational wave subgroup and the multi-wavelength follow-up subgroup. And here is a list of people that has primary affiliation to this subgroup. I happen to be the contact for this subgroup. And each of these subgroups has a person that is called the MAF, the math engineer. Is the person that is able to use the math software to extract information from the simulations, from the OPSIM, and understand how well as LSST can do depending on what is your goal. So there is definitely a lot of things that we are trying to do in the next months and years. There is space for contributions. So this is just to say that if you're interested to join, you can simply go on the website and submit your application, and we'll be very, very happy to hear more voices. So among the things that we are trying to do, we are working on is studying what is the best strategy for LSST to go after gravitational waves. So that's something that's very relevant today. Okay, I also wanted to stress a little bit of what we have been doing, so a little bit of a historical perspective. So our priority 1 year ago was to have TO capabilities on LSST. So at this meeting, you heard from Tony that this seems to be happening. But that was not so clear until recently, I would say. So our primary objective, our primary goal as part of the multi-wavelength follow-up and rotational wave follow-up team was to have this capability in place on LSST. And we are happy to see that it's going to happen. And as part of this effort, we wrote a little chapter on the white paper. The white paper in LSST is a live document that everybody can have access to. And this was 1 year ago when we were trying to convince everybody that if we were not, if we don't have TO capabilities on LSST, we would just miss out on very beautiful science. So just to give you an idea, and this is the place where if you're interested to read all the white paper, here is a link. So I heard a little questions about why we cannot just rely on the main survey. So why we have to use TOs to start with. And you can do a very simple exercise and just use the delta T, the median internight gap in the Y filter, just to understand how, in how many cases, just by chance, using the main survey, we would just land on the same patch of the sky within 1 week, which is the very minimum requirement to understand if there is a kilonova or not. And if you do this exercise, you'd find out that only 7% of the sky would satisfy this very, very basic requirement. This is just to say that if you put a little bit of more work and try to understand, okay, so now I have 2 data points in the Y filter in 1 week. What if I want to know more? What if I want have color information or what if I want to know in how many cases I do cover the entire gravitational wave localization region? You put everything together and you would find out that if you only use the main survey, you would have a probability of 1 to 3%, a few percent, that's what you have. So this is the main reason why we actually need TO capabilities if we want to use LSST to do some relevant science with gravitational waves. So yeah, that was the main motivation for TOs. So what what are we up to now? What are the things that we are trying to accomplish within the subgroup? So the one thing that we want to understand better is to try to understand with numbers how well we would be doing depending on which filters we decide to use, when to repoint. So depending on the strategy, how well we would be in finding the counterparts. We are also interfacing with brokers. You heard, maybe we're going to be hearing about brokers later. So that, because it's very, very important for the community to let the brokers know what is the key information that they have to give us for us to do the best scientific job. And the other thing that we are trying to do within the subgroup is to identify collaborators outside LSST. So go beyond LSST and try to speak to people on the radio part of the sky, SKA, people on the high energy part of the sky, try to really put all the facilities that we have at work and try to do the best science we can. So along this main theme, I'm gonna tell you something about multi-wavelength observations so coordinated with LSST. So we heard co-observing, we heard joint observations, follow-up, everything. I want to consider everything. I just mean let's just observe the same field of LSST either before, at the same time, or after. So why is that important, and what can we do? This is extremely important. You understand first to understand better the nature of the transients that we're looking at, but also it can be strategic. So we can decide based on what we find at other wavelengths. We can decide how to prioritize our LSST fields. That is the basic idea. So at this meeting, of course, we heard about the optical transient sky, and we already heard from Wenfei that if we do a good job in the radio part of the sky, we might actually have some new information that might tell us, yes, that is the counterpart, or no, that is not the counterpart of our gravitational wave. So since I thought that the X-ray side of the sky was a little bit neglected, I decided to give a little perspective of what is going on the X-rays. And here you have a picture of all the possible X-ray transients that we know about right now, luminosity versus variability time scales. And we heard already a couple of times that the X-ray sky is kind of quiet compared to the optical sky, definitely quiet compared to that one. And I happen to have been involved with 3 mission concepts that have something in common. The common property is that we try to have a wide field X-ray instrumentation. So our goal will be to have the X-ray part of the sky do the same job and same thing that is happening in the optical and in the radio with SKA. So there are three experiments that I'm aware of. So the first is STAP, is the Transient Astrophysics Probe. That's the mission that Krista was speaking about before. PI is Jordan Camp, and it's a NASA probe category, and it has been selected for study. Another mission that is happening on the American side is STAR-X. STAR-X is a MIDEX, so it's a smaller mission, and we submitted the proposal. We are waiting to hear back about STAR-X in the second half of 2017, and PI will join. And on the European side, there is also kind of similar effort. It's THESIUS, led by Lorenzo Amati, and this is an M5, ESA M5. It's a medium-sized mission. So I'm going to tell you a few features of each of these instruments, and then try to understand how well they would be serving our purpose to identify possible counterparts of gravitational waves. So in the X-ray world, and I'm now referring to neutron star mergers right now, we have 2 possibilities. We have the collimated component, the jet, and then we have the isotropic component. We already heard about that yesterday. And since the isotropic component is a little, from the observational perspective, I would say we do not have a clear cutting edge case. I'm very sorry for the supporters. I'm not gonna say anything about it. So we will concentrate on the jets. So the basic idea here is that, so we have our neutron star merger produces a jet along one line of sight. This is collimated, which is not good. However, it happens that even if we are not on axis, we are off axis, we still have some chances to get the signal. It just happens to peak at later times and be also a little fainter. And here I just put where Swift XRT, the sensitivity of Swift XRT goes. This is for something at 200 megaparsecs. So you do understand that Swift XRT is not the machine that we use to find off-axis counterparts. And of course, the off-axis counterparts are the most promising ones because we do not have to be lucky and be along the line of sight of the jet. So that is why we're most interested in this kind of features. So this is where the quasi-isotropic component would be there, or high luminosity. So it would be very, very nice if it's there. So very powerful. So this is a few features about Star X. So it's the MIDEX mission. The field of view is 1 degree squared, and it goes pretty deep. And now I'm gonna tell you how deep it goes. So if we put Star X on this plot, here is where we get with 2 kiloseconds exposure, which is the typical one. So you do see that we can easily find counterparts that are 35 degrees away from the on-axis side, which means 50% of the time. So 50% of the times, this is what we would be seeing, and we are able to find it. And this is instead my understanding of the MAXI sensitivity compared to Star X. So for MAXI, we would have to rely to be on the line of sight of the jet. What about Theseus? Theseus is the European mission. It has 3 different instruments. The beauty of Theseus is that it does combine an infrared telescope, which is what we want if we want to find the actual novae. However, the wide field instrument, X-ray instrument, is a lobster eye technology, which means a little shallower than what you have if you use CCDs and the usual optics. And if you were to put Theseus on this plot, you would see that Theseus would help us mainly if we are on axis, but it's not as sensitive when it comes to off-axis components. And here is the TAP mission, which I believe is the most promising of one of the 3. It is so TAP has many 4 different instruments. So it does as the lobster module, so something which is kind of shallow, 10 to the minus 11 in terms of X-rays. It does have an infrared telescope, and look at this. This is the wide field 1 degree square, so it's actually beautiful to do this kind of science. And it does have an X-ray telescope that the XRT, which are similar to Star X, the Star X that you saw before, is here. And there is also a gamma ray detector, the GTM, that there are actually 3 of them. That is going to be the one that is going to be detecting the short gamma ray burst ones.
So if TAP is finding that the other 2 are not necessary as well?
I would say, yeah, but there is also, so let me also say that in terms of time scale, if Star X is approved, it's going to happen in 2023. If this gets approved, it's not going to happen before 2029, 2023. So that's my understanding. So I would say that this is something when I read the proposal, I felt this is really what we want. The timing is maybe a little late, but yeah, this is fantastic.
What's the time frame for Theseus?
It's say 2030.
Okay, so but if this happens, that doesn't make any sense.
Europeans might not say that.
Am I allowed to say that? I'm in both teams, so I'm not yeah, it's yeah, anyway. So and this is how if you put the lobster at the top, the two instruments, the lobster one and the X-ray telescope is where we go. So it's again we would be able to see 50% of the neutron star mergers with wide field
Can I
X-ray.
ask a quick question about that? You said that the field of view of the X-ray telescope is 1 square degree. On an off-axis burst, you're not going to get the burst until you reach a point. So how are you going to?
So yeah, this is dreamland when the localization of gravitational wave would be 20 degrees squared, and we can do tiling.
I see.
What's the I should know this. What's the exposure time to get to that?
I
With the
don't
X-ray
remember, but
telescope?
it must be, I don't know, I would say 2 kiloseconds, 1 kilosecond, I guess, yeah. So that is not an issue, it's really the field of view that is the thing. So our idea is to do tiling and find the counterpart.
So if the LIGO error region stays at 100 square
It's
degrees,
hard.
you're really in trouble here.
Yeah, I'm in trouble, yes.
2029 is not going to be 100. I hope.
For someone who doesn't know any better, what are the practical limitations in terms of expense or design or whatever that prevents you from doing 10 square degrees of that sensitivity?
Oh, this thing?
Yeah, that's at 1. Can you do 10? Like, is it twice as much, 100 times as much?
So there is always a trade-off between field of view and sensitivity, and the X-rays are extremely hard to get down to this kind of sensitivities with 10 degrees squared. That was, that's my dream, but the only way to get to very wide field of view is to change their optics.
Okay.
So, and then you go into the field of lobster eye technology, which gives you very wide field of view, but then all of a sudden your sensitivity goes there. I say it's a technological limitation right now.
It's basically how you focus. You know.
And X-rays are
Yeah,
hard.
you have to use grazings in one way or the other, so it's a different geometry.
And the good thing about TAP is also that the same instrument, the same satellite, also carries the infrared telescope, which also has the 1 degree field of view. So you can imagine that you can get at the very same time the infrared information and the X-ray information. So that would be fantastic. And maybe couple that with the LSST information. Let's see what else. Yeah, so this is the dream that we have, is that this is the localization region of gravitational waves. With LSST, maybe we're gonna find all of these sources, and then our dream would be to combine these sources detections to ancillary information from other wavelengths, so X-rays or radio, so that kind of thing would trim down considerably the number of sources that we would then concentrate on follow-up. So that's our dream. And that's basically all I wanted to say. Let me just restate once again that if you're interested in joining the LSST science collaboration, please do. We need help. That's it.
Thank you, Ron. Any questions?
Thank you.
Well, just because we were talking about timescales now, so yet another mission on a closer term, and this is actually what Krista was referring directly to, is this Tau ISS mission. So that is more modest, but it's a wide field imager of 360 square degrees. It's like what's on TAP, but one module like that. But if that's a mission of opportunity to join the space station. So if that were to be funded, that could be ready for launch in 2021. So that's kind of more in the time scale that we've been talking about today, and that's what is pending, decision.
But if that has a similar sensitivity to what Raffaella has just shown, it's sensitive to gamma ray bursts, not to off-axis.
Correct. That's the 10 to the minus 11 hertz per thing.
Right.
So it's that same.
So
basic idea.
what you get over Fermi GBM is better localization.
Well, and you can, or just serendipitously in your, it's one quarter of the sky, or you follow up the GBM on I follow gravitational, yeah, waves.
So Peter, is it easier cost to orbit to go to ISS than just to a satellite? So somehow there is a preferred route there. So it's more likely to happen on a shorter time scale.
It's cheaper, and you basically have the power. You have the constant the constant data link.
So you don't have to carry everything.
Yeah, you don't need your own space. I mean,
Yes.
you can. But it's a more modest mission, but anyway,
Can I just make a comment from the theoretical standpoint? Well, there have been this nice work calculating off-axis afterglows for certain jet geometries, like the stuff Andrew showed. I think there needs to be more effort to explore how sensitive these models are to different structures of the jet. Because I feel like a lot of these missions, like we're relying on the predictions for off-axis jets. Like Svi said earlier, maybe there's a question as to why we haven't detected orphan afterglows yet. And I think it would just be better to have a few more models available for different structures. I think to get a sense of what the uncertainties are in some of these models. I'm not criticizing the ones available, I'm just saying that they assume a particular, like a top hat where the jet is uniform through some angle as opposed to has some angular structure. This could make a big difference.
Would be my earlier assertion that if you want to have something that's good at detecting gamma ray bursts, the gamma ray mission is helpful, and we could focus on better gamma ray localization. Would be another way of getting to this answer.
Okay, thank you. So we're going to continue with Eliu from Illinois. So thank you, Eliu.
Yes, thanks for the invitation. So I want to talk about what has been going on having these two paths merging at some point. This is gravitational waves and LSST. So just to give you some perspective of where I'm coming from in the next slides, NCSA has a broad program in connection to gravitational waves. We have a strong background on analytical and numerical relativity. We are the main data hub of DES and LSST data. And we also host Blue Waters, which is the most powerful supercomputer in any university campus. XC, we also have the National Data Service, and we have some other programs that are critical for a variety of collaborations. So let me just take a step back and try to size the problem that we are trying to tackle. On gravitational waves, we have heard in the last 2 days that the main problem is not related to, for example, data transfer. This is almost trivial in the standards we have these days. The problem we have is related to the higher dimensional parameter space we need to cover, both in terms of detection and parameter estimation. There are other challenges that David mentioned and Chad as well, related to modeling and detection of these systems. We are right now targeting a very narrow region of parameter space, was a circular spin-aligned and anti-aligned systems. That's not enough. Challenges that are coming up, intercontinental transfer, when we have detectors in 4 continents. It's not only about technology, but politics. And also, when you try to expand existing searches, that is complicated. Now, for LSST, you have a problem with data transfer. Maybe it's not a problem because they have a dedicated network that they will not share with anybody else. We also need to understand how to combine the cadence of observations with EM follow-ups. Now, this is a big challenge. The high volume of triggers that will be released to the public or to astronomers. And a big challenge, you need to classify this in real time. Now, based on how LSST is going to be tied in the sky, the question is whether we will have enough information to construct luminosity curves with the level of detail that we need to associate that with gravitational wave counterpart. And of course, as Tony showed yesterday, the parameter space is not well covered, so we will have a lot of discoveries down the road. Now, in terms of the signals that we are trying to detect, in this paper we show that right now in LIGO we don't have an algorithm to detect eccentric compact manner equalescence. So we have been working on that for a while, and this year we released the first model that can target a wide region of the BBH parameter space for really asymmetric systems. It can reproduce state-of-the-art quasi-circular systems, or models, and at the same time, it can reproduce eccentric numerical relativity simulations. So we now have a model to try to go and target these systems, which is really good. Now, the problem with this is, in these plots, I'm showing you the fitting factor, which is the overlap between two waveforms maximized over a template band. And here I have 8,000 eccentric injections for these combinations of masses and this initial eccentricity. And I'm using a bank of spin-aligned EOB waveforms to try to recover these signals. And here you can see that these stars represent the two transients that LIGO has detected. And what this means is that these systems can have up to this value of eccentricity and still be recovered with existing algorithms and waveforms. So what this means is that they may have had this value of eccentricity at 10 Hertz or 14 Hertz and still be misclassified as quasi-circular systems with our algorithms. Now the issue with this is that to do the recovery, since we have an additional dimension, you need to use about 1.5 million templates. Now, can you do this in real time? It's really challenging. And remember, I'm not still using spins. So this is going to increase the number of templates that you need.
We're doing 600,000 now on a rack this big. No problem.
You think? Okay, good.
I think we should question why, though. I mean, out of the floor, like, what's the probability that anything matters is going to be eccentric? I understand with black holes binary structure or something, but
so look at this region of parameter space. This is the BBH, NSBH region of parameter space. 0.1 in eccentricity is very low, and it is astrophysically motivated. And with this very low value of eccentricity, the fitting factor is around 0.88.
But 0.1 is not low because GR will radiate all the eccentricity away very, very quickly.
Not always.
No, not always.
For dynamical mergers can be
But
much
dynamical
harder.
mergers for neutron stars?
NSBH.
It's less common, yes.
NSBH.
Okay.
It can happen.
All right, so what we have so far is this. We have detectors that have some issues, as Barry mentioned in the morning. Right now we have a good handle on vacuum simulations. The theory has been developed for about 100 years, and we have made some discoveries. Now, if you are interested in numerical relativity, this is just an act. We're going to host this meeting at NCSA. So if you want to learn to play with numerical relativity codes, consider attending. So now let's move forward. These are just some ideas based on eccentric simulations. If you need 1.5 million templates for eccentric non-spinning, now consider how many you will need for eccentric spin processing. Right now we have 300K templates, and people are thinking about reducing the size of the template banks. So is this model sustainable? So Open Science Grid is a clever idea to use high-performance computing resources. You just redirect the jobs so that you don't have to install your code cluster-wide, and then you use the computational power in those centers. But this can only go so far. And when you want to do accurate parameter estimation to inform the astronomers that they can follow up an event, then you need to provide some good information. Now, let's just compare this with what the NSF is predicting in terms of HPC centers. By 2024, the improvement will be about a factor of 20. Now, right now, when you apply for exit time, you get at most 60% of what you request, if you are lucky. Many people really know how to use these clusters, like people doing Corpo labs or BNS studies. We can scale this a lot, but what will be our priority in the future? And is it really necessary to go and flood these centers with LIGO data analysis? That's just a question. Now, match filtering is very expensive. It is the tool that enables discovery, but it is good to think whether it is still the paradigm that we need to continue using in the future for higher dimensional parameter space. And the other question is, as Chad mentioned in the morning, we may have some sources that are in the LIGO data that we're simply not extracting because we have not been using the templates, or maybe the algorithm is not good enough. And the other thing is, more detectors will join the array in the near future, sensitivity will increase, the length of the templates will increase, the computational